Hello. In this video, we define eigenvalues and eigenvectors. We'll start with this motivating example to get an idea of why they're important and what they are. Let's consider this matrix 1, 2, 2, 1. Well, it's not too hard to see that when I multiply any vector AB by that matrix, I get 1, 2, 2, 1 times AB, which is equal to A plus 2B and 2B plus A. Let's use these to just compute a couple other vectors. If I apply this matrix to the vector 2, 1, for example, I get A is equal to 2 and B is equal to 1, but there's a 2 in front. Then 2B is yes, we get 4, 4. Right, A is 2 plus 2B makes 4, and then, oh, I wrote the same thing twice, sorry. The second row is 2A plus B. Okay, now this makes sense, and this is a 5. If we were to plot this vector, we would have something like somewhere around there. That would be 4 or 5. Let's try to do another vector just for fun. If I have A equals -1 and B equals 0, I get -1, and then I get 2A, which is -2. So if I were to plot this one, this would land somewhere down there. So the point of these vectors is to show you that the matrix, it's a little hard to understand what this matrix is doing. However, there's a couple special vectors that behave very well with this matrix. Let's try to compute A times 1, 1. If I plug 1 and 1 in for A and B here, I get 1 plus 2, which is 3, and I get 2 plus 1, which is also 3. And maybe I want to rewrite this as 3 times 1, 1. So when I end up drawing this vector, it will be a rescaling of my vector 1, 1 by a factor of 3. Similarly, when I plug in this other vector here, 1 minus 1, I get 1 plus 2 minus 1, and then I have 2 times 1 plus -1. The result of this is -1, 1, which is -1 times 1 minus 1, which is the vector I started from. In other words, this vector here is, well, it's negated. So it's actually multiplied by -1 by our matrix. So these two vectors here are special in that they satisfy the following property. Multiplying the matrix by the vector is the same as multiplying the vector by some scalar c. The scalar is different. In this case, it's equal to 3, and in this case, it's equal to -1, but it tells you something about these two vectors. They don't get sent somewhere around like the green and the red vectors up here. They get actually stretched or maybe reflected over and stretched in the negative. Whenever we have a vector that behaves like this, such that matrix multiplication is the same as rescaling it, we call that vector an eigenvector, and the corresponding scalar c is called an eigenvalue of A corresponding to V. So that's our definition. To make it more precise, here it is. Given a square matrix n by n, a vector in Rn that is non-zero is called an eigenvector if there is some scalar lambda such that A times the vector v is equal to lambda times the vector v, in which case we say that lambda is an eigenvalue corresponding. So to recollect what we did in our previous example, where A was 1, 2, 2, 1, in this new terminology, we can say the following. The vector 1, 1 was an eigenvector with eigenvalue 3, and the vector 1, -1 was an eigenvector with eigenvalue -1. What about the vector 2, 2? Well, if I multiply 2, 2 by the matrix A, 1, 2, 2, 1, 2, 2, I get 6, 6, which is 3 times 2, 2. So this tells you that eigenvectors are not unique because 2, 2 is an eigenvector with eigenvalue 3. So it's another eigenvector with the same eigenvalue 3. Let's have a look at the last example, just to familiarize ourselves with the definition. I give you a matrix A and a vector, -1, 1, 2. The problem is claiming that this is an eigenvector. Let's check that and let's find the corresponding eigenvalue. So the way we can make sure what the eigenvalue is by just multiplying the matrix by the given vector. It's 1, 1, 2. When I compute this, I get 2 times -1, -6 plus 12 in the first entry. Then I get -1 plus 9 minus 12 in the second entry. And then I get 2 plus 16 minus 26 in the third entry. Cleaning this up, we get that this is 4. This is 9 minus 13 is -4. And this is -10 plus 2, -8. So the eigenvalue, by looking at this vector here, we notice that it's -4 times the initial vector, -1, 1, and 2. In other words, the corresponding eigenvalue is -4. In the next few videos, we'll see how to compute eigenvectors when we know an eigenvalue. And then lastly, we'll see how to compute the eigenvalues of a matrix.